Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS Group. In this video, I will discuss about infinite series. The name of the subject is Mathematics 3, subject code is BSC301, and this is for the students of Computer Science and Engineering and Information Technology. Module number is 1. So, to learn infinite series, you need to know what is sequence, and in my previous video I have already discussed about sequence. So now I will start infinite series. So what is an infinite series? So let UN be a sequence, okay? Then the sequence Sn defined by S1 equal to U1, S2 equal to U1 plus U2, S3 equal to U1 plus U2 plus U3, and so on. Okay, Sn equal to U1 plus U2 plus up to UN. This is the nth term. Okay, so like this, if we continue, this is the definition of the sequence Sn. Now it will be represented by the symbol U1 plus U2 plus ... So this is an infinite series. U1 plus U2 plus U3, this will continue infinitely. So this is said to be an infinite series, is said to be an infinite series generated by the sequence Sn. Okay, so generated by the sequence UN. So if we are given a sequence UN, then we will generate a new sequence that is named Sn. So what will be the terms of the new sequence Sn? This will like S1, first term will be the first term of the sequence UN, that is U1. Okay, second term will be the sum of first term and second term. S3, third term will be U1 plus U2 plus U3. Like this, the sequence will continue infinitely. So if we go on like this way, so U1 plus U2 plus U3 plus ... it will go continue infinitely. So this summation is said to be the infinite series, and from which we are getting this infinite series? We are getting from the sequence Sn, and it is generated by the sequence UN. So this is called the infinite series generated by the sequence UN. Okay, so if we are given a sequence, we can find an infinite series corresponding to that sequence. Okay, so this infinite series is denoted by summation UN, where n equal to 1 to infinity. So this is the notation of the infinite series. So the elements Sk of the sequence Sn are called partial sums, are called partial sums of the infinite series UN n equal to 1 to infinity. Okay, so this is the infinite series, and if we take any certain term, that is I have denoted it by sk. So k is an arbitrary natural number. So suppose we are taking s5, so it will be u1 plus u2 plus u3 plus u4 plus u5. So this type of terms are called partial sums of the infinite series any summation n equal to 1 to infinity un. Okay, so this infinite series summation un can be convergent or divergent. So when it will converge or diverge. Okay, now I will tell you. So this series, infinite series, summation n equal to infinity un, summation n equal to 1 to infinity, will converge or diverge according as the sequence Sn converges or diverges. That is, if we want to determine that an infinite series is convergent or divergent, then we have to know the sequence, corresponding sequence Sn is convergent or divergent. If the sequence Sn is convergent, then the infinite series will be convergent. If the sequence Sn is divergent, then the infinite series will divergent. So convergence and divergence of this infinite series will depend upon the convergence and divergence of this sequence Sn which we got from the sequence un. Okay, now we know how to determine that a sequence is convergent or divergent. If a finite limit exists, then we can say that the sequence is convergent. That is, if limit n tends to infinity, Sn equal to suppose s, which is a finite real number, then this sequence Sn convergent, and hence this series will convergent. And if this sequence is not convergent, that is a limit n tends to infinity Sn is not a finite real number, then this sequence will be divergent, and hence this infinite series will divergent. Okay, so this was the definition of infinite series. So to determine the convergence and divergence of an infinite series, we have to know first the sequence Sn is convergent or divergent. That is the sequence of the partial sums which were generated by the sequence un. Okay, now I will give you some examples. So example number 1. Example number 1 is 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus ... So this is an infinite series. We have to determine that this series is convergent or divergent. Okay. Now, what is the what will be un here? What will be un here? Un will be 1 by, that is nth term of the sequence un. It will be 1 by n into n plus 1. Okay, so Sn will be 1 by, Sn is actually S1 plus S2 plus ... up to Sn. So here Sn equal to u1 plus u2 plus ... up to un. That is partial sums of n terms of the sequence un, first n terms of the sequence un, and that will be 1 by 1 into 2 plus 1 by 2 into 3 plus ... up to 1 by n into n plus 1. So this is Sn. Okay, now these terms can be written as 1 minus half, this will be equal to half, plus this can be written as half minus 1 by 3, and this will be equal to 1 by 6. Okay, similarly in this way this is written as 1 by n minus 1 by n plus 1. Okay, now you see that all the terms like minus half, plus half, minus 1 by 3, plus 1 by 3, these terms will be cancelled out, and there will be remaining two terms, that is the first term and the last term, 1 minus 1 by n plus 1. Now for the checking of the convergence or divergence of this series, we have to check that the sequence Sn is convergent or divergent, and for that we have to check that limit n tends to infinity Sn is finite or infinite. That is, limit n tends to infinity Sn is limit n tends to infinity 1 minus 1 by n plus 1. So this will be equal to 1 because this is 0. So here we see that limit n tends to infinity Sn is equal to 1, which is a finite real number. So we can say that this sequence is convergent. This sequence is convergent, and hence we can say that this infinite series, the given infinite series is convergent. Okay, so this is the procedure how to check an infinite series, it is convergent or divergent, using the definition of series. Now I will give you the second example. Example number 2 is 1 plus 2 plus 3 plus 4 plus dot 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 up to n. This is an infinite plus dot dot dot. This is an infinite series. So see, if we write un, that is nth term of the sequence un, this will be n. Okay, now what will be Sn? Sn is u1 plus u2 plus dot 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 up to un, that is partial sum of the first n terms of the sequence un, and that will be equal to 1 plus 2 plus 3 plus dot 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 up to n. This is equal to Sn. Now we have to check that the sequence Sn is convergent or divergent. For that we are finding the limit n tends to infinity Sn, that is limit n tends to infinity. So Sn is 1 plus 2, that is sum of the first n natural number, and we know that sum of first n natural number is n into n plus 1 by 2, and it will be equal to infinite. So limit n tends to infinity, Sn is infinite. So this sequence Sn is divergent, and hence we can say that the series summation n equal to 1 to infinity un is divergent. Okay, now next example number 3 is 1 plus half square plus dot dot dot. So this is the infinite series. So un will be the nth term of the sequence un, that is 1 by 2 to the power n minus 1, because u1 is this, that is 1 by 2 to the power 0, u2 is 1 by 2 to the power 1, so un will be 1 by 2 to the power n minus 1. Then what will be Sn? Sn will be 1 plus half square plus dot 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 up to 1 by 2 to the power n minus 1. Okay, now we have to find the limit of Sn when n tends to infinity, that is limit n tends to infinity, this term. Now you can see that this is a GP series. Okay, this series in geometric progression. Now what is the common ratio? Common ratio is 1 by 2, half. So sum of first n terms of a GP series, we know that a into 1 minus r to the power n by 1 minus r, where a is the first term, r is the common ratio. Okay, so limit n tends to infinity, a is the first term, that is 1 into 1 minus r is half to the power n by 1 minus half. Okay, so this will be equal to limit n tends to infinity 2 into 2 into 1 minus 1 by 2 to the power n. Okay, now if we simplify it, limit n tends to infinity, it will be equal to 2 minus 1 by 2 to the power n minus 1, because 2 is multiplied with this term. So 1 by 2 to the power n minus 1. So this will be equal to 2, because this will be 0. So the limit is 2, which is a finite real number. So we can say that the sequence Sn is convergent, and if Sn is convergent, then we can say that the series summation n equal to 1 to infinity un is convergent. Okay. Now I will give you another example. We are doing all these sums. We are checking the convergence and divergence using definition. Okay. So next example is example number 4, and that is 1 minus 1 plus 1 minus 1 plus 1 dot dot dot. Now here you can see that this is an infinite series. Now what will be un? Un will be minus 1 to the power n minus 1. Okay, so this is the nth term of this series, nth term. If n equal to if you put n equal to 1, that is minus 1 to the power 0, it will be 1. If n equal to 2, then the second term comes, and that will minus 1 to the power 1, that will minus 1. In this way these terms will come. So Sn will be 1 minus 1 plus 1 minus 1 plus dot 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 plus minus 1 to the power n minus 1. So what will be the sum? What will be the sum? So Sn will be 0. Okay, Sn will be 0 if n is even. Okay, if n is even, and the sum will be 1 if n is odd. Okay, so it is clear from this sum. If n is even, then all 1, that is plus 1 minus 1, will be cancelled out, and the sum will be 0. And if n is odd, then the one single one will remain, and that will be the sum. So here we are getting two sums of two result of this summation depending upon the nature of n. If n is even, then we are getting one sum, and if n is odd, we are getting another result. So this is clear that the sequence Sn is not convergent, that is, it will be divergent, and hence the series summation un is divergent. Okay. Now till now I have discussed the definition of infinite series and 4 examples, and we have discussed about the convergence and divergence of the series. But we have determined it using definition of series. Now I will tell you some test. Okay, test for convergence and divergence. There are some tests for checking convergence or divergence of infinite series. If we apply those tests to check convergence and divergence, then it will be easy than applying the definition. Now I will start the discussion about the tests. So tests for convergence. Okay. So number 1, P series. This P series is a certain form of series that is called P series, the definition of P series is a positive term series of the form summation of 1 by n to the power p. This all the terms will be positive of this series, and the form will be like this, 1 by n to the power p. This is called P series. This series is called P series. I am not writing the range of n, it will n equal to 1 to infinity, since this is infinite series, called P series. This series is called P series. Is convergent. This forms this series will be convergent if p greater than 1 and divergent if p less than equal to 1. So P series will be convergent if p is greater than 1 and divergent if p is less than equal to 1. Suppose we are taking an example. Suppose we are taking this series 1 plus 1 by 2 plus 1 by 3 plus dot dot dot. Okay. So here if we write this series using summation, this will look like summation 1 by n. Okay. N equal to 1 to infinity, summation 1 by n. Now here the power of n is 1, that is p equal to 1. So this is a P series. This is in the form of this. So this is a P series where p is equal to 1, and according to the condition, if p is equal to 1, then this series will be divergent. So this series is divergent. So just watching the P series, we can say that the series is convergent or divergent, because you can just seeing the P series, you can determine the value of p, and the convergence and divergence of P series depends upon the value of p. Okay. So next, number 2, comparison test. This is very important. Comparison test. Okay. So this test states that if summation un and summation vn be two series of positive terms such that limit n tends to infinity un by vn equal to L, where L is a non-zero finite number, a non-zero finite number, obviously real number, where L is a non-zero finite real number. Okay. Then these two series converge or diverge together. So if you are given two series un and vn of positive terms, and if this limit exists means if the value of the limit is a non-zero finite real number, then we can say that these two series converge or diverge together. That is, if un converges, then vn converges, and if un diverges, then vn diverges, or vice versa. Okay. Now I will take an example of this comparison test. So the example for comparison test, let us check the convergence of this series summation of sine 1 by n. Okay. So we have to check the convergence of this series. Now, so un equal to sine 1 by n, and the series, infinite series is this summation sine of 1 by n. So un equal to this, and we are taking vn equal to 1 by n. Okay. So we are taking this series 1 by n Vn. Yes. Okay. So next, according to the statement of comparison test, if we have two series, summation un and summation vn, where un equal to sine 1 by n, vn equal to 1 by n, then we have to check limit n tends to infinity un by vn. That is, limit n tends to infinity sine 1 by n by vn is 1 by n. Okay. Now we know that the result of this limit will be 1, which is a non-zero finite real number. Okay. So we can say that summation vn and summation un converges or diverges together. Okay, from this non-zero finite real limit, when we get that the limit is non-zero finite real number, we can just say that summation un and summation vn converges or diverges together. Okay. From this we can't say that summation un is convergent or divergent. Just we can say that these two series converges or diverges together. Now we have to check the convergence of this series, that is summation of un. Now since we got this conclusion, then if we can check the convergence of summation vn, that is if we can determine that summation of vn is convergent or divergent, then we can say that summation of un will be convergent or divergent. Okay, so summation of vn, that is summation of 1 by n, it is a p series. Just I discussed about it. It is a p series where p equal to 1, and if p equal to 1, we know that a p series is divergent. Now since summation of vn is divergent, then from this line we can say that summation of un is also divergent. Okay, so this was the example of comparison test. So you will be given just summation of un. So watching the un, you have to take vn in such a way that you can find this limit. And you have to know the convergence about the series vn, otherwise you can't tell about summation of un. Okay, so if you know the convergence of vn, then using that and comparison test you can tell about the convergence of un. Okay, so next test I will tell you, Cauchy's root test. Okay. Next test, number 3, Cauchy's root test. Okay, so the statement of this test is, if summation un is a series of positive terms such that limit un whole to the power 1 by n equal to L, a finite real number, then number 1, summation of un converges if L less than 1. Number 2, summation of un diverges if L greater than 1. And number 3, the test fails if L equal to 1. Okay, so from Cauchy's root test we can check the convergence of and divergence of a series in this way. So if the limit un whole to the power 1 by n is L, which is a finite real number, and if L is less than 1, the series is convergent. If L is greater than 1, the series is divergent, and if L equal to 1, this test fails. From this test we can't conclude anything, so we have to apply another test. Okay, so now we are taking an example of Cauchy's root test. Summation n equal to 1 to infinity 1 plus 1 by root n whole to the power minus n to the power 3 by 2. So we have to check the convergence of this series. Okay, so here un equal to 1 plus 1 by root n whole to the power minus n to the power 3 by 2. This is un. Now we will find this limit, that is limit n tends to infinity un whole to the power 1 by n. So this is equal to limit n tends to infinity un is 1 plus 1 by root n whole to the power minus n to the power 3 by 2, and that whole to the power 1 by n. So this will be 3 by n to the power 3 by 2 into 1 by n, and 3 by 2 minus 1, that is half. So after doing un to the power 1 by n, this comes. Okay, and this is equal to limit n tends to infinity. From this term we can write this like as 1 plus 1 by root n whole to the power root n. 1 plus 1 by root n whole to the power root n. Okay, now I will do here. Now since we know this result, that limit n tends to infinity 1 plus 1 by n whole to the power n equal to e, we know this result. Using this result from here, and we know that if n tends to infinity, then root n also tends to infinity. Okay, so 1 by 1 plus 1 by root n whole to the power root n, and this will be equal to 1 by e. Now we know that the value of e lies between 2 and 3, so 1 by e will be less than 1. Since the value of e is less than between 2 and 3, lies between 2 and 3, and this is a proper fraction, so 1 by e will be less than 1. Now according to the statement of Cauchy's root test, we know convergent if this limit, the condition was the limit should be finite real number. 1 by e is a finite real number, and the finite real number, if it is less than 1, the series is convergent. If it is greater than 1, then the series will be divergent. Now here our limit is less than 1, so we can say that summation un is convergent. So in this way we can check the convergence and divergence of a series using Cauchy's root test. Now it may happen that this limit becomes 1, then if it is equal to 1, then we have to write that Cauchy's root test fails. We can't conclude anything from by applying this test. We have to apply another test. So I will discuss more tests. Okay, so next test is D'Alembert's ratio test. Number 5. D'Alembert's ratio test. So this test states that if summation un be a series of positive terms such that limit n tends to infinity un plus 1 by un is equal to L, a real number, finite real number, then number 1, summation un converges if L less than 1. Number 2, summation un diverges if L greater than 1. And number 3, if L equal to 1, the test fails. Okay, so Cauchy's root test, just this forms is different from Cauchy's root test. This will be un plus 1 by un. We have to find this limit. If the limit is finite real number, then you have to check that it is less than 1 or greater than 1, and according to that we can say that the series is convergent or divergent. Okay, now I will give an example. Okay, so the example is summation n equal to 1 to infinity n factorial by 2 to the power n by n to the power n. Okay, so we will test the convergence of this series. So here un equal to n factorial into 2 to the power n by n to the power n, and we have to check the limit n tends to infinity un plus 1 by un. We have to find out this limit, okay, according to the test of D'Alembert's ratio test. Now if un equal to this, then un plus 1 will be n plus 1 factorial into 2 to the power n plus 1 by n plus 1 to the power n plus 1. Just we put n plus 1 in place of n. Okay, so now we are putting the values of un plus 1 and un here. So limit n tends to infinity un plus 1 is n plus 1 factorial. Okay, I'm writing here. So limit n tends to infinity un plus 1 by un equal to limit n tends to infinity un plus 1 is n plus 1 factorial 2 to the power n plus 1 by n plus 1 to the power n plus 1, and by un. So I am writing the reciprocal of this. So n to the power n by n factorial into 2 to the power n. Okay, so equal to, now this n plus 1 factorial and n factorial, now cancelling out, it will be limit n tends to infinity n plus 1, now 2 to the power n plus 1 by 2 to the power n, that will be into 2, and the remaining portion is n to the power n by n plus 1 to the power n plus 1. Okay, and no, okay, so here from here 1 n plus 1 will be cancelled out. So this will be equal to limit n tends to infinity 2 into n to the power n by n plus 1 to the power n, and from here we can write that 2 by 1 plus 1 by n whole to the power n. Okay, so I have just write this from this term. You can simplify, you will get this term. Okay, so okay, you can see that this is n by n plus 1 whole to the power n. Now I have written this as 1 by, and I have written the reciprocal of this. Okay, so this will give us this term. Now as we know that the value of this will be e, limit n tends to infinity 1 plus 1 by n whole to the power n equal to e, so it will be 2 by e. Okay, now since the value of e lies between 2 and 3, so this is a proper fraction, that is 2 by 2 point something, and that will be less than 1, and according to D'Alembert's ratio test, if the limit is a finite real number and if it is less than 1, then the series will converge. Okay, so since the limit is finite real number and less than 1, so the series will converge. So the series will be convergent. Okay, so in this way we can check the convergence of a series using D'Alembert ratio test. So in this video I will discuss there are many tests to discuss, so I will continue this discussion in my next video. So till then you watch this video and try to understand the tests and definition of series. Okay, so in the next video I will discuss the remaining tests and I will give you the assignments so that you can solve. And till then, if you have any query regarding this video and if you face any problem when you watch this video and try to understand this, so you can contact with me. My contact details is given in the first of this slide. Thank you.